In the history of aviation, there has never been a plane more groundbreaking than the B-2 stealth bomber. Capable of flying anywhere in the world undetected, the B-2 can arrive over its target, release precision munitions, and escape confident in the fact that the bombs will hit their targets and that the plane will return home safely. Revolutionary in design and capability, the B-2 represents the culmination of many disciplines and sciences, from aeronautics to stealth to bombing itself. It also has a distinction unshared by any conventional aircraft. For the entirety of its service life, the B-2 has never been detected, targeted, or engaged. The B-2 is flown exclusively by the United States Air Force and is the most sophisticated flying machine in existence. Its creation relied on 100 years of bombing experience, the evolution of computers, radical jumps in engineering science, new approaches to aircraft design, and a new generation of weapons called smart bombs. Among the personalities involved were a visionary American aircraft designer and an unrecognized Soviet physicist. The story of the stealth bomber begins during the first days of bombing. Early World War I bombers were neither purpose-built nor particularly sophisticated. Aviation was in its infancy, and bombs were often carried aloft in the pilot's lap to be tossed by hand at targets on the ground. Technology had advanced by the time World War II began. Faster bombers carried heavier weapons over targets protected by early warning radar, anti-aircraft guns, and high-speed interceptor aircraft. By 1944, two distinct schools of tactical bombing had emerged from the war above Europe. After suffering staggering losses during daylight bombing raids, the British conducted their bombing at night. Small bombers called Mosquitoes would be launched in the general direction of a target. Spitting fire from their engines, the Mosquitoes would proceed without radio contact or formation towards the vicinity of the target. Flying high and in the dark, these small bombers were very hard to detect. Far ahead of the main bomber force were bombers designated as pathfinders. These planes were flown by the best navigators in the Royal Air Force. Their mission was to drop incendiary bombs on the target, producing bright flames and creating an easily spotted target for the main bomber force. Bombers would then head toward the fires, drop their bombs, and individually make their escape. This decentralized approach, with British bombers coming from all directions to bomb one target, was difficult to defend against. By contrast, the United States relied on daylight bombing raids consisting of hundreds of bombers in tight formation. The B-17 was an enormous plane, with a crew of 10 and defended by 13 50 caliber machine guns. In fact, the B-17 carried so much weight in machine guns, ammunition, and defensive gunners that its bomb load was the same as that of the two-man Mosquito. Escort planes didn't have the range of bombers, which meant the big planes were usually over targets with little protection. Although gun turrets protruded from every side of the B-17, the slow, tightly packed fleets of bombers proved easy targets for the fast, heavily armed German interceptors. Because they dropped their bombs as one, the bombers flew in complicated formations, designed so that they didn't drop bombs on each other. Advancements in fighter technology, as well as enormous industrial output, were the two factors that allowed the U.S. to turn the tide of the bombing campaign. Under the cover of new escort fighters, the 8th Air Force began launching bomber missions in excess of 1,000 bombers, with 600 escort fighters. British Mosquito bombers suffered a fraction of the losses endured by the B-17s. While the British approach demonstrated how effective bombing could be when utilizing bombers that were difficult to detect, The U.S. would continue to use large bombers in high-altitude formations until the 1960s.
It would take whole fleets of aircraft to fly over a single factory or a single bridge, dropping tons and tons of bombs with the objective of destroying that one bridge or destroying that one factory.
Following World War II, vast sums of money were spent on bigger, faster bombers with larger payloads. The United States had powerful new weapons and an equally powerful new enemy, the Soviet Union. In the event of an all-out war, the U.S. needed a new bomber that could carry the enormous atom bombs deep into the heart of the USSR. Two radically different designs emerged to answer this call. Built as a flying wing, the YB-49 could carry the same bomb load as a larger bomber, using less power and thus less fuel. Built by visionary aircraft designer Jack Northrop, the all-wing design reduced drag almost completely. Although initial tests were favorable, it was too far ahead of its time. The trim efficiency of the YB-49 lost out to the brute force of the enormous Convair B-36. Powered by 6 massive pusher propellers and 4 jet engines, the B-36 was one of the only aircraft of its day capable of reaching the Soviet Union. Defended by 16 20mm cannon mounted in computer-controlled retractable turrets, the B-36 was the largest, most heavily defended U.S. bomber ever built. Although it required more crew and more fuel than the YB-49, the huge B-36 was an imposing bomber with an enormous 86,000-pound bomb load, 14 times the capacity of the B-17. The B-36's enormous bomb bay made it the only aircraft capable of carrying the newly developed hydrogen bomb. Despite its success as a bomber, the B-36 had been conceived in the early days of World War II. By the early 1950s, as jet fighters and missiles began to appear in the sky, the B-36 became obsolete. As engineers stripped out the B-36's complicated defensive gun turrets, Boeing delivered the B-52. The B-52 became the mainstay of the U.S. strategic bombing force and continues to be a formidable aircraft today. Powered by 8 turbojet engines clustered into 4 pods, the B-52 had ample room along its wings for the newly developed cruise missiles. The wings were swept back like a fighter to reduce drag, and were so long they needed landing gear at the tips. Bombing tactics hadn't changed since World War II. Large fleets of heavy bombers flew in high-altitude formations to targets, released weapons as one, and returned home. Conventional wisdom told military planners that the Soviet Union couldn't engage targets over 50,000 feet. Altitude, not guns, would keep the bomber fleet safe. In 1960, the Soviet Union shot down a U-2 spy plane, which had been flying at 70,000 feet. In the event of an all-out war, a bomber assault at 50,000 feet was doomed. The answer was to fly low and come in under the radar. Limited by terrain and the horizon, ground-based radar detects incoming aircraft in a cone-shaped pattern. The higher an aircraft is, the farther out the radar can detect it. By flying at low altitudes, bombers could delay detection and reach their targets with less resistance. Most U.S. bombers had been designed to penetrate enemy airspace at high altitudes and supersonic speeds, and were completely mismatched for the task of low-level flight. The exception was the B-52. After some minor updates, it proved to be a very stable low-level bombing platform. The new tactics were more successful than high-level bombing had been, but the lumbering bombers still required massive amounts of support and escort planes to successfully complete their missions. In 1972, the U.S. began the Linebacker II bombing raids. Designed to bring the North Vietnamese to the negotiating table, B-52s hammered North Vietnam around the clock for 12 days. The sophistication of Soviet-supplied air defenses in the north meant that over half the planes launched during the bombings were support or escort planes. Some planes filled the sky with clouds of aluminum strips called chaff that confused ground radar. Other planes, called wild weasels, intentionally drew fire so that they could respond with special missiles designed to home in on defensive radar and surface-to-air missile sites. Based on the scale of the North Vietnamese air defenses, and the fact that the Soviet Union would certainly employ an even more sophisticated system, conventional bombing raids against the Soviet Union appeared impossible with the B-52. A new bomber was needed. The Rockwell B-1 Lancer seemed to be the answer. Designed for supersonic flight at low altitudes, the B-1 was fitted with a special terrain-following radar that maps the ground in front of the plane and lets it fly at less than 100 feet. Although it flew very low and very fast, the B-1 was still susceptible to detection by radar. At the same time as the B-1 was being developed, a small group of scientists was designing a revolutionary aircraft that could not be detected by radar. They called it the stealth fighter. The new aircraft could leisurely enter enemy airspace, drop its payload, and exit unharmed. Designed on the limited computers of the early 1970s, the F-117's strange shape allows it to deflect radar signals away from targeting systems, rendering it extremely difficult to detect. Although it can carry only 2 smart bombs, the stealth fighter proved its effectiveness in the early minutes of the 1991 Gulf War, when flights of stealth fighters destroyed Iraq's entire command, control, and missile defense network without being detected or engaged. The next evolution of stealth was called the Advanced Technology Bomber. It incorporated research gleaned from the stealth fighter program, plus numerous new features. These included a decreased radar cross-section, lower acoustic noise, a small visual profile, decreased electromagnetic emissions, and a decreased infrared signature. The official term for all of these features is Low Observable, or LO. Officially unveiled in 1988, the ATB would come to be known as the B-2 Spirit and would enter service in 1993. Nearly impossible to detect, the stealthy B-2 can carry a wide variety of weapons on internal rotating launchers. These launchers let the B-2 carry any combination of cruise missiles, smart bombs, and sea mines. Smart bombs are assigned targets by computer and are guided by satellite, meaning the B-2 can engage as many as 16 different targets simultaneously. Its low observability, mixed with the unique weapon delivery system, means the B-2 can arrive over a target with no warning, release 16 different weapons, destroy 16 different targets, and leave without the enemy knowing what happened. When it rolled onto the tarmac at Palmdale, California, the Flying Wing bomber carried the name of Jack Northrop's company and had exactly the same wingspan as his 1943 bomber, the YB-49. Standing at the podium, the Master of Ceremonies said simply, "Jack Northrop, we salute you." The term for all the things that make the B-2 the stealth bomber is Low Observable, or LO. LO is made up of radar cross-section, infrared signature, appearance, electromagnetic signature, and acoustic signature. Although stealth aircraft seem to be a new invention in air combat, there are many documented attempts at stealth from as early as World War I. The German heavy bomber Linke Hoffmann R-1 had part of its fuselage constructed from transparent Cellon. Although the plane made its debut too late in the war to study its effects, the plane itself represents some forward thinking in the arena of low observable. In 1944, American soldiers discovered the unfinished German Horten H-09 flying wing bomber. Incorporating a number of forward-thinking features, this LO bomber had jet engines buried in the fuselage, a long exhaust path, a radar-absorbent covering, and a flying wing shape which gave it a diminished radar cross-section. These features would all resurface on the B-2 over 50 years later. An LO bomber that did fly during World War II was the de Havilland Mosquito, which flew only at night. To keep costs down, it was built of balsa wood. While this was viewed as a step backward from the all-metal bombers being produced at the time, the wooden construction reflected less radar energy than aluminum and lent the aircraft a very diminished radar signature. This, combined with its small size, made the Mosquito very difficult to detect. Its overall losses were a fraction of the B-17's. Another approach to avoiding detection was by flying at extremely high altitudes. Built by Lockheed's famed Skunk Works, the U-2 spy plane flew above 60,000 feet, while the SR-71 flew on the edge of space, 95,000 feet, at 3 times the speed of sound. Both aircraft incorporated radar-absorbent coverings and radical designs to reduce their radar cross-sections. The Lockheed Y-03A silent observation plane ignored radar detection altogether. The guerrilla tactics used by the North Vietnamese Army relied on sound to detect approaching enemy aircraft. Although not stealth to radar, an enormous muffler allowed this plane to loiter silently above the jungle treetops for hours, relaying troop and supply movements undetected. Each of these aircraft represents a small step forward in a specific area of low observability. This succession of little steps culminated in the B-2, which is a revolution in all fields of low observability. The most common method of detection is radar, which is an acronym meaning radio detection and range. Radar was developed during World War II as a means for directing and countering aircraft at night. These early radars proved quite useful in defending England from German nighttime bombing raids. The theory is simple. A radar transmitter sends out radar waves which bounce off things and scatter in all directions. Some of the scattered energy is reflected back to the radar site. The reflected radar energy is collected by a receiving antenna. Most modern radar dishes combine the 2 antennae, alternating between transmitting and receiving. Things which reflect radar are called targets. By feeding information about the intensity of the reflection, as well as its angle, into a computer, the location of the target can be plotted. Unfortunately, radar does not necessarily distinguish between types of targets, so it is really only useful for detecting aircraft, where there is nothing else around for the wave to reflect off of. Although less detectable bombers had proven their efficiency in World War II, there was still no scientific method for decreasing an aircraft's radar cross-section. Despite the LO characteristics of U.S. spy planes, the U.S. could not build a stealthy strike aircraft. It was an academic paper from the Soviet Union that would change all this. Pyotr Ufimtsev was an obscure Soviet physicist who just happened to discover the secret of stealth. Ufimtsev published a paper which dealt with determining deflection angles of radar waves. Radar waves behave similarly to light waves. The law of reflection states that a light ray will reflect off of a surface at the same angle at which it encountered the surface. Thus, to get a return, a radar reflection requires a surface that is perpendicular to the incoming wave. A sphere provides the largest radar cross-section because it has an infinite number of tangential surfaces. Thus, the sphere always has a perpendicular side to any angle. While most energy directed at a sphere is deflected, the small amount that is always reflected back makes the sphere detectable from any angle. By contrast, a flat plane is only detectable from a 90-degree angle. At any angle other than dead on, a flat plane will deflect all radar energy away from the radar site. At one angle, the plane presents the largest radar cross-section, but at all others, the smallest. Unfortunately, flat planes are not aerodynamic. For aircraft, the best compromise between the flat plane and the sphere is a curved shape with a variable radius called a continuous curve. This shape allows aerodynamic flow without the sphere's infinite number of tangential surfaces to reflect radar. Inexplicably, the Soviet Union allowed the paper to be published and apparently didn't pursue any sort of stealth aircraft program. An American scientist used Ufimtsev's paper to develop a computer program called Echo-1, which could calculate the radar cross-section of crude shapes. This gave engineers a tool for designing a stealth strike aircraft. Work began in secret to discover ways to manufacture aircraft based on Echo-1 calculations. The lack of computing power in the 1960s and 70s meant that Echo-1 couldn't calculate the radar cross-section of curved shapes. The curved designs of the SR-71 and U-2, which had reduced radar cross-sections, had been obtained largely by accident. The restrictions of those early computers meant the first stealth aircraft would have to be built out of flat planes. Flat planes present a design challenge because they are not aerodynamic, and if perpendicular to a radar site, they are extremely detectable. Designers determined that the biggest threat to strike aircraft is ground-based radar. As a result, the stealth fighter was designed specifically to deflect radar waves coming from below the aircraft. The result was the F-117, the first aircraft to carry the unofficial designation stealth. Advances in computer technology and research into stealth would eventually allow the computation of continuous curved shapes for reflecting radar, which would ultimately yield the flying wing-shaped B-2.
The shape of the B-2 is basically designed so that it minimizes the amount of radar that can be returned to the original source, and by, unlike the 117, which uses faceting to redirect the radar, it either absorbs it or in some cases it redeflects it a different direction.
Like the F-117, the B-2's shape was designed from the beginning to reduce radar. Unlike the F-117, however, the B-2 deflects radar from any angle.
The primary reason it's shaped the way it is to help deflect the radar away from the originating source. So once the radar beam hits the B-2, it's actually deflected into another area where the originating radar is not, so that it doesn't pick up the signal that it sent out. Therefore, it's stealthy.
The B-2 also makes full use of radar absorbent materials, or RAM.
RAM is basically radar absorbing material, so it does actually absorb the radar waves, keeping them from reflecting off of the aircraft.
Although the true composition of RAM is secret, it's likely it is made of lossy materials that contain free electrons which, when bombarded by radar waves, vibrate and convert the radar energy into heat. The result is that radar energy is dispersed across the skin of the B-2, rather than being reflected back to enemy radar sites.
RAM can be a number of things, to the way the aircraft is constructed and how those materials fit together and interact with each other, to a single layer of coating that we apply to the aircraft.
English and American scientists developed RAM during World War II, although they didn't quite realize its potential. Designed to deflect and absorb radar, RAM is an important element in modern stealth aircraft. But during World War II, RAM was applied to submarine periscopes and in radar testing facilities. In a few cases, the antennae on ships were coated with RAM to prevent them from being detected as targets by the ship's own radar. but RAM was never applied to aircraft. To further reduce the B-2's detectability, other elements of LO are implemented. To reduce the noise of the B-2, the engines are buried deep within the airframe, turning the body of the plane into a gigantic muffler. Next to radar, the heat signature of an aircraft is the easiest to detect.
Heat is used in a combat situation primarily to defeat an aircraft through its exhaust, and as an aircraft is flying through the air, it also generates a heat signature. A lot of modern missiles and can pick up on those heat signatures and use those to target a vehicle. Therefore, we try to defeat that as a means of detection as well.
Although the skin of an aircraft may not be hot, the boiling air produced by the engine's exhaust creates a contrail, which acts like a beacon. To correct the heat problem, the B-2 incorporates a long exhaust path, heat-absorbing tiles, and a dual air intake system. Below the main engine air intakes are smaller bypass intakes. The air from these intakes is diverted around the engine and mixed with the hot engine exhaust. Once this mixed air leaves the engines, it passes over heat-absorbing tiles. These same tiles are used on the space shuttle to protect it from the intense friction in the atmosphere on re-entry. The exhaust path is long and above the wing. It's not visible from the ground. The result is that the air behind the aircraft, as visible from the ground, is much cooler than when it comes out of the engine and produces no contrail. Although its existence is unknown, the B-2 may make use of a radical new technology known as radar-absorbent structures. If radar-absorbent material is a sponge for soaking up radar energy, radar-absorbent structures are a vacuum. A radar-absorbent structure is based around a hollow structure, most likely a honeycomb. The open sides of the honeycomb face out on the aircraft and are covered with the aerodynamic radar-absorbent material. Radar waves strike the ram, but instead of being dispersed, most of the energy is transmitted through the ram and into the honeycomb. Inside, the radar bounces off the inside of the honeycomb, which is coated with RAM. Each deflection decreases the radar's energy somewhat. Even if the radar could get a solid reflection, the end of the structure is blocked by the outer RAM coating, trapping the radar energy inside.
It's a living, breathing aircraft. It sweats. Moisture and other things develop inside the aircraft. Anything that develops inside the structure of the aircraft comes out through the weep holes. And so there are little tiny holes in the airplane that allow moisture and other things that develop inside the wing to come out, and it maintains the structural integrity of the aircraft.
The result is that the radar energy is completely absorbed into the structure of the aircraft, and absolutely no reflection is possible. Although there is no proof that radar-absorbent structures exist, if they do, the B-2 may very well be completely invisible to radar. This represents what is known about the B-2's stealth design and capabilities. What truly lies beneath the skin of the B-2 will likely remain classified for a long time to come. When air approaches a wing, it is forced in two directions, up and down. This creates a high-pressure area above the forward portion of the wing and below the wing. As the wing slopes away, a low-pressure area is formed above the remainder of the wing. This low-pressure area lifts the wing up. In addition, the high pressure below the wing pushes it up.
It's all about lift and drag. An airplane has wings, and what those are, another word for them is airfoils. As air travels over the wing, it creates a pressure differential between the top of the wing and the bottom of the wing. And what that produces is lift, as the low pressure seeks the high pressure area.
Traditionally shaped aircraft have two large wings supporting a central fuselage. Stabilized at the rear, with a horizontal stabilizer and a vertical stabilizer, or tail. Although advances in computer technology have allowed the fuselage to be more efficient, it still produces a great deal of drag. This drag not only decreases performance in terms of speed, it also requires large wings and engines burning lots of fuel to lift it off the ground and to keep it there. The reduction of fuselage drag, combined with an overall increase in lift, is the flying wing's primary advantage. The flying wing is also called a lifting body because the body of the plane does just that.
The advantages to the wing design, to the flying wing design over a traditional aircraft is the replacement of that fuselage with more wing. So that creates a bigger surface area of wing, which translates into more lift.
Instead of the traditional arrangement, the entire volume of the aircraft is contained within the wing. This eliminates fuselage drag and vastly increases overall lift. The difficulty with flying wings has always been stability. Jack Northrop's flying wing was notoriously dangerous, and in theory, all flying wings share the same inherent risks. A flying wing is stable in terms of pitching up or down, or banking left or right. What the flying wing does not inherently counteract is yaw. Yaw is the tendency of a plane to fishtail left or right. On traditional aircraft, the horizontal and vertical stabilizers are mounted on the tail of the plane, placing a great deal of control at the end of what is essentially a long lever. A flying wing doesn't have this lever, and thus control surfaces must be far more complex. To compound the control complications on the B-2, there are no vertical surfaces whatsoever. Northrop's YB-49 and XB-35 both had vertical stabilizers. The B-2, however, does not have this luxury. Most bombers have enormous tails, which act like billboards when struck by radar waves. Instead, the B-2 controls its roll, pitch, and yaw, all with the same set of complex control flaps on the rear of the wing.
For everyone who's seen a B-2, the one thing that you notice right off the bat that's missing is that vertical tail, the vertical stabilizer. Without computers, there's no way we could fly the B-2. The computers actually sense the environment around the aircraft as well as the pilot's inputs and keep the aircraft going.
The flight control computers sense the air loads using things like those air data ports over there that sense static pressure and aerodynamic pressures on the aircraft, what its angle of attack is, what its side slip. All those inputs go into a flight control computer. The flight control computer then makes adjustments to the flight controls faster than the pilot could by hand, enabling the flight control computers really produce that stability that we lost with the tail.
The outermost control surfaces on the B-2 are the rudders, which also function as brakes. Twin flaps move in conjunction to make the bomber yaw left or right. When the flaps on both sides are extended both up and down, they act as a speed brake. These flaps aren't effective when fully closed, so during normal flight, they're left slightly open. This does increase the radar signature, and during combat operations, the B-2 is flown with the rudders fully closed. Moving inboard from the rudders is where the elevons are located. Elevons are a combination of ailerons and elevators. Ailerons and elevators control the pitch and roll of an aircraft. On most planes, the ailerons are located on the trailing edges of the wings, while the elevators are located on the horizontal stabilizer. The ailerons act in opposite directions of one another to roll the airplane, while the elevators act together to pitch the plane up or down. On the B-2, the elevons perform both functions through combinations of movement. If all the elevons pitch up or down, the aircraft will pitch in the opposite direction. If the left elevons pitch up, while the right elevons pitch down, the bomber will roll to the left, and vice versa. The coordination of all these flaps is the job of an amazing technology known as fly-by-wire.
Fly-by-wire takes inputs from the pilot and other aircraft sensors, feeds them into a series of computers, which then produce an output to a hydraulic actuator, which moves the flight controls for us.
Because the computer's job is to make the aircraft perform according to the pilot's controls, any external forces that act on the aircraft, such as wind gusts, are counteracted automatically by the computer. This allows the B-2 and other fly-by-wire aircraft to maintain the traditional controls and maneuvers common to all aircraft, despite its radical design. The radical design of the B-2 represents a step forward in all arenas of aircraft design. The result of fly-by-wire is that while pilots compare flying a B-52 to driving a bus, the B-2 handles more like a sports car. The B-2's mission is to penetrate heavily defended areas, drop precision-guided munitions, and extract itself without ever being detected.
That'd be the ultimate capability, to be able to go in undetected and leave undetected. However, there's one unique aspect of all bombers. If you're going in, you're more than likely going in to drop something. So right off the bat, as soon as bombs start going off, someone's going to know there's an aircraft in the sky. So as you're leaving the country, really what you're looking for now is that ability to sneak back out of the country.
The power of stealth was demonstrated fully in the 1991 Gulf War. F-117A Nighthawk strike aircraft destroyed military targets deep in the heart of Baghdad without ever being detected. At the time, Baghdad had the most sophisticated grid of interlocking defensive and anti-aircraft radar systems ever fielded. During the course of the war, F-117 aircraft engaged targets in Iraq 1,271 times and lost 0 aircraft. This was due almost entirely to the F-117's stealthy radar cross-section. That the B-2 has an even smaller radar cross-section with less detectable LO characteristics, paired with a bomb capacity 8 times that of the F-117, is a testament to its potential.
The B-2 is a stealth aircraft. It's designed to basically kick down the door to open up that entryway for other aircraft.
Any B-2 mission begins with planning. Positions of known radar sites, as well as any missile sites and intercept aircraft, have to be plotted. The B-2 deflects some radar and absorbs some radar, but it's not impervious. For this reason, B-2 pilots must determine the best route through known radar positions, known as the corridor.
The B-2 enables us to pull the wool over the enemy's eyes and significantly darken his view. So with that in mind, there may be advantages to making different turns and going different directions en route to the target with the bomber to enable us to accomplish the mission.
The amount of radar an aircraft reflects is called its radar cross-section, or RCS. As aircraft approach radar sites, they encounter more radar energy, which increases RCS. This means that an aircraft which is undetectable at long range becomes detectable at close range. Defensive radar networks are set up around strategic areas using multiple radar sites. The size of an aircraft's radar cross-section and its proximity to the radar site determines when it can be detected. All of this is taken into consideration so that the individual radar site zones of detection overlap, effectively creating a wall of radar. Because the B-2's radar cross-section is so much smaller than all other military aircraft, it can only be detected at extremely close range. Thus, the overlapping zones of radar which detect all other aircraft are useless against the B-2, and the radar wall develops holes through which the B-2 slips. Once over the target, the B-2 releases bombs which are individually targeted and self-guiding.
Typically, like I said, we knock the door down, we go in first and lead the way for other aircraft with a larger radar signature to come in and strike targets to drop those unguided weapons.
Thus, The B-2 can arrive over its target unannounced, release fire-and-forget weapons, and leave craters as the only evidence of its presence. It is only fitting that the most sophisticated bomber on Earth carries the world's most sophisticated arsenal. The B-2 can carry anywhere from 80 500-pound bombs to 8 5,000-pound bunker busters. Other options include sea mines, stealthy cruise missiles, and just about everything in between. The crown jewel in the B-2's arsenal is the 2,000-pound JDAM. JDAM stands for Joint Direct Attack Munition, but it's commonly shortened to Smart Bomb. The JDAM comes in a variety of weights, from 250 pounds to 5,000 pounds, although each variant has the same basic purpose: to deliver a high-powered explosive punch with pinpoint accuracy every time. A JDAM is made from a free-fall bomb, a strake assembly which adds stability, and a tail kit which contains satellite guidance equipment and the fins which steer the bomb. JDAMs can be programmed on the ground before they are loaded into the B-2, or they can be reprogrammed in flight to accommodate changing target conditions. The B-2 carries its weapons in a manner different from most other bombers. Where B-17s and the original B-52s carried their bombs stacked in racks to be released en masse, the B-2 uses a rotary launch assembly. When the pilot wants to drop a bomb, the bomb bay doors open, the assembly rotates to the correct position and drops the requested bomb. This allows the B-2 to carry different types of munitions, or bombs programmed for specific targets in the same bomb bay, and provides a connection between smart bombs and the B-2's computers. In the air, the B-2's onboard computers and the computers in the JDAM are linked, providing the smart bomb with up-to-the-minute information about target position and weather. During the B-2's 40-hour flight, targets may move, winds may shift, or storms may move in. The JDAM uses this information to correct its course and to assure maximum impact with minimal civilian casualties. The strake assembly and tail fins on the JDAM act like wings, giving it a gliding range of just under 8 miles. All the B-2 must do is pass within 8 miles of its target, and the JDAM will take care of the rest. Once the JDAM is released from the B-2, its guidance is internal. An extremely accurate satellite guidance receiver in the tail homes the JDAM in on its target. If the satellite guidance fails, the JDAM has an inertial guidance system backup. Accurate to within inches, it is the same system used on U.S. submarines for navigation. The most common load on the B-2 is 16 2,000-pound JDAMs. New technology called the Smart Bomb Rack Assembly will allow the B-2 to carry 80 smaller 500-pound JDAMs. This is over 4 times its previous capacity. Missions that would have required 5 B-2 flights now only require 1 because, for most targets, the 500-pound bomb is just as effective as the 2,000-pound bomb. The B-2 carries many other amazing weapons, including the AGM-158 stealth cruise missile. Angular in shape, the 158 is nearly invisible to radar. The 5,000-pound bunker buster is a variant of the JDAM, designed to penetrate deep into the earth and release a devastating explosion. From 500-pound smart bombs to stealth cruise missiles, the B-2 has the versatility to carry just about any weapon, anywhere on Earth, and deliver it with precision accuracy every time. The B-2 bomber has proven its effectiveness time and again. Through its use of low observability and smart weapons, the B-2 can engage targets with more accuracy, less civilian damage, and more safety for the pilots than any other aircraft in the world.